Here we have a sideways parabola defined parametrically using the equations x equals t squared and y equals t plus 2. We can see that when t equals 0, x equals 0 and y equals 2. So that's a point right here when t equals 0. And when t equals 1, x equals 1 and y equals 3. That's this point right here. And you can notice this little bitty arrow right here is indicating the direction of this curve. So here is t values that are negative, negative, negative until t equals 0. And then t goes positive, and we've got this top half of the parabola. So the question now is, can we find the slope at these two t values? Well, at t equals 0, it should be pretty obvious that we're going to get an undefined slope. But how do we do that analytically? Remember that when we're looking for slope, we're looking for, well, traditionally we're looking for derivatives, but the slope is not just the derivative of any old equation. The slope is the rate of change of y with respect to x. And we don't have x and y defined together. We have x and y both defined in terms of a third variable, t. So what happens if we take the derivative of this equation? Well, if we take the derivative of x equals t squared, well, we're going to realize that t is our independent variable. So we're going to take the derivative of x with respect to t. So that's going to give us dx dt on the left side of the equation. And then the power rule just tells us we get 2t. And you might say, well, what about the chain rule? But when we take the derivative of t with respect to t, we just get 1. Okay, so that's how fast x is changing as t changes. Right? The other part of this is that y equals t plus 2. So when I differentiate this equation with respect to our independent variable t, we get dy dt equals, well, the derivative of t with respect to t is 1. And the derivative of 2, well, 2 is a constant. 2 is not changing ever, so the derivative is 0 as always. So we have two different rates of change. Okay, so if x is changing at this rate and y is changing at this rate, and we want to know how fast y is changing with respect to x, why don't we just divide and say dy dx is equal to the rate at which y is changing with respect to time divided by the rate at which x is changing with respect to that same variable time. All right, so that's going to be, let's see, we've got a 1 in the numerator and a 2t in the denominator. So looks like the derivative of y with respect to x is 1 over 2t. An interesting answer because we've got y's and x's over on the left side, but we only have t on the right side. But let's see if that actually works. Dy dx evaluated when t equals 0 is 1 over 2 times t, but t is 0. So 2 times 0, so that's undefined. There we go. Okay, so undefined, which is exactly what we expected at t equals 0. What about at t equals 1? You might not know what this is off the top of your head, what the slope is here, but we definitely know that it's positive. So we can do dy dx evaluated at t equals 1, and we get 1 over 2 times 1 equals 1/2. All right, so I can accept that. That seems reasonable. If we take this point and we go up 1 and right 2, rise of 1, run of 2, and we draw a line connecting those two. Oops, let's try that again. I can buy that. That looks like a tangent line to me. So this seems reasonable. Let's see if we can check this using a more traditional approach, right? We know that we can replace t with y minus 2 in this equation, and that's what we've done here. And we can find the derivative of this instead. So if we want to know what dy dx is, the slope is dy dx, we'll take the derivative of this equation with respect to x, and we get 1 equals 2 times y minus 2 raised to the 1 times, don't forget the chain rule, we're taking the derivative of y minus 2 with respect to x, that's going to be dy dx. All right, so let's see, that's going to be 1 divided by 2 times y minus 2. Wait a second, isn't y minus 2 the same thing as t? Sure is. y minus 2 is the same thing as t, so this is actually the exact same derivative. So when t equals 0, we are at the point x equals 0, y equals 2. So when we evaluate dy dx when y equals 2, we get 1 over 2 times 0. Same as before, right? Because when you plug in 2 for y, you get 0. Okay, so this seems to be bearing itself out. And then dy dx when t equals 1, well, that's the same thing as the point 1 comma 3. So when y equals 3, we get 2 times y minus 2, but that's 3 minus 2, that's 1. Aha! Okay, so that's good news. We've found the slope using two different methods, and we got the same answer. So turns out this is not a fluke. This process of taking dy dt divided by dx dt to get the slope is in fact how we find the derivative of parametric equations. Or at least that's how we find the slope, which is one sort of derivative that we can find. And then we can also generalize this to the second derivative. When we take the derivative of our derivative, we have to take the derivative of our first derivative with respect to time, but because this is not dx, we also have to divide by dx dt. This part right here shows up for the second derivative, so it's something that's easy to forget, so I'll say, don't forget. It's essentially the chain rule, so don't forget the chain rule. All right, so let's see if we can find that second derivative here. So the second derivative at these points, well, let's give this a try. We know that dy dx equals 1 over 2t. So we're going to take the derivative with respect to x of dy dx, which is going to be, well, let's rewrite this. Let's write this as 1/2 times t to the negative 1. That's going to make it easier for us to differentiate. So we have that 1/2. And then we're going to take the derivative of this with respect to x. So that's going to mean bring that negative 1 out front, drop the exponent by 1 down to negative 2. And since we're taking the derivative with respect to x, the chain rule says multiply that by dt dx. Oh, well, that's actually the reciprocal of dx dt. So multiplying by dt dx is the same thing as dividing by dx dt. Aha, there we go. So this first part is going to be negative 1 over 2t squared, right? Because the negative 1/2 and the t to the negative 2, that drops down to the bottom. And then instead of multiplying by something we don't know, we're going to divide by something we do know. Remember, we know what dx dt is. We found that earlier. Dx dt is just 2t. So this is going to equal negative 1 over 2t squared times another 2t. So 2 times 2 is 4, t squared times t is t cubed. All right, so if I can now use that information to evaluate the second derivative, we can say that d squared y dx squared, evaluated at t equals 0, is negative 1 over 4 times 0 cubed, which is undefined. Okay, well, that might make sense because the first derivative was undefined. It also might make sense because our concavity looks like it's changing at that point, right? We've got maybe a concave up part right here. We've got a concave down part right here. So maybe there's no concavity here. So that might make a little bit of sense. Now, when we find the concavity or the second derivative at t equals 1, we expect to get a negative answer because it's concave down. So let's see what we get. We get d squared y dx squared evaluated at t equals 1 is going to be negative 1 over 4 times t cubed, where t equals 1. And that's going to give us the negative answer of negative 1/4. Fantastic.